If someone is late and passing this camera, please don't move it, because then only part of the whiteboard will be visible. I will talk to the off-campus coordinator. If he agrees to put these recordings online, then we can put it on Moodle. It's huge files, you need a good internet connection to download them. It's not a replacement for the actual lectures. And yeah, what else? It may be not reliable, quality is not great, and it may happen that someone stumbles and there's no recording, or the battery runs out, something. So I can't promise to have them for every lecture, and I can't promise to have them in a satisfactory quality. And well, of course, it does not replace the actual lectures, but it is probably the next best thing to the real lectures, in case you have to miss one. So I was asked about where to find assignment 0. Assignment 0 and all the assignments are in the study guide, which you will get a printed copy in the first tutorial, or here on Moodle study guide starting at page 25, and also at the so-called Turing website, the other website, which I don't know if there is a link. Here, if you click here, then you get to the Turing website. The good thing about this Turing, it's very simple, and we have been using this for a long time, when there was no mentioning of Moodle and things yet. And it works quite well and is very reliable. So this is why we duplicate the material and have them also here. Assignment problems. Here are also the due dates, starting with number 0. So we continue about sets. We yesterday introduced sets. It is a bit of an abstract notion, and you may ask the question, why do I need it? Nowadays, sets occur, and set terminology occurs very much in every internet search. Actually, think of a search as looking for a set of web pages with a certain keyword in it. You may sometimes enlarge your search, or you may want to restrict your search. You may want a search which has that or that keyword in it, which means you combine the set of the internet contents which has keyword A and keyword B, say Math120, keyword 1, keyword B, UNE. You want everything which has Math120 in it and everything which has UNE in it, which is probably not a smart thing to do, because you get a huge amount of web pages. You probably want, so that would be called the union of the two sets. So a set A and a set B, you can form the union, and the union is a new set which has everything in it, what was any element which was in A and anything which was in B. So for internet contents, anything which had Math120 in it, and anything which has UNE in it. And the logic description would be or. It has this or that in it. And you get a larger set. So let me demonstrate this with our number sets. So if say A is a number set, say having 2, 5, and 10 in it, and we have another number set which has 2, 4, and 6 in it, So maybe I can find another pen. So then what would be, that's much better, the union, this symbol, think of this symbol as a cup in which you put everything is in it. So this is the, or as a letter U for union, A union with B is now the set which has any element in it which is an element of A or an element of B. So we can start, it definitely must have any elements from A in it, 2, 5, 10. So anything which is in A is in it, and now we look what we have in B. We have a number 2, element 2, but we have it already, we do not need to duplicate it. We have an element 4, it wasn't in A, so we have to add it, because it is in B. And number 6 also is in B and was not in A. Sets are not ordered, so the order doesn't matter. Here I wrote it down just in the natural order, here also. Here it doesn't have the natural order, but it doesn't matter. In sets we do not care about the order in which we write the elements. It's just any list. And this set would be the same set as if I had ordered it. Order does not matter. Also, there was a couple of questions on Moodle, people getting confused with the different kinds of brackets. These curly brackets are used just to list the elements. If you see a set described in curly brackets, then what you see is what it is. It is the set of these elements. Here of 3 elements of all these elements. Now, yesterday I also considered a different kind of set, say using a different letter, X instead of any capital letter is good, using different kind of brackets, the angular brackets, not the square brackets. So say from 2 to 6. On the number line, this is everything between any number, any real number, starting from 2, including 2, ending at 6, including 6, and anything what is in between, 2.1, 2.11, 2.00, pi, which is approximately 3.14. That's all in this interval. So that's an infinite set. We have infinitely many elements. We can't even list them. And we describe it in this way in the square brackets. And say another set, y, from 3 to 8. Maybe I should get a different color here. So say from 3 to 8, this is 3, this is 8. So this is y. What do you think is the union of these two sets now? Anything which is either an element of the black set or an element of the blue set should be pretty simple. Something green. So we start here. This is in the set because this is in the black set. This is in the set because it is as well in the black as in the blue set. This is all in the set because it's in the blue set. So we go from here from 2 to 8. From this to that. So the result is again an interval. The union x and y, x union y, is again an interval which starts at 2 including and ends at 8. Here the two intervals which we formed the union of, they overlapped. It could also be, say, we have 2 intervals which do not overlap. say from 5 to 7, then we can depict the union. The union would be the set of any number which is here or it is here, but we cannot write it as a simple interval or so. So there's no way to write it in an easier way. Here we can simplify it. It's again an interval. If we form the union of two intervals which do not overlap, then that's just the union. There's not much else we can say about this. Another operation we do with sets is the intersection. We can intersect two sets. Then instead of that strange U-like symbol, we have it reversed, upside down. And if we think of our internet search, we are now looking for Math120, and at the same time we want that in this piece of internet contents we also have U and E in it. Which means we are looking for a set where the element is at the same time in A and in B. A and in B. So going back to our listed set here, the intersection of A intersected with B. A way to do is the following. We are looking for all elements which are elements of A and B of the same time. We just browse through the elements of A and look if it is also in B. 2 is also in B, so it comes into the intersection. The first element of A is also in B, so we take it. Element 5, we look in the set B, it is not in the set B, so it's not in the intersection. Number 10 is in A, but it is not in B, so it is not in the intersection. So in this case, the intersection consists of only one element. The only one element which is common is this number 2. By the way, there is also a notation which I haven't introduced yet. If 2, for instance, in this case, is an element of A, there is a shorthand to write this. It is, I think, comes from the Greek letter epsilon. It's a little like an E or a Greek epsilon, but if I write it in this way, it means 2 is an element of A. Also, we can write 2 is an element of B, and therefore 2 is an element of the intersection. 5 is an element of A, and 5 is not an element of B. So we can use also this notation to cross this element sign and then denoting that 5 is not an element of B, and therefore 5 is not an element in the intersection because it's not an element of B. There was some discussion on Moodle saying that if say X is an element of R, this just means it's another way to say X is a real number. X is an element of the set of real numbers, means X is a real number. So for instance, we can say 5 is a real number in this way. 5 element of R, 5 is a real number. We can write A is not, well, as a say Math120 is not an element of R, because this is not a real number. So now let's look at the intersection of intervals, the intersection of x intersected with y, always look at this number line. We start, so anything which is left from 2 is neither in the set of x nor in the set of y, so it can't be in the intersection, it's in neither of the sets. So anything starts at 2, and here we have a little interval, little segment of numbers which are in x but not in y. It's black but it's not blue. So x but not in y, it is not in the intersection because it is not in y. So here, starting from 3, we have numbers which are at the same time blue and at the same time green. So they are in the intersection, including 3 and 6. But then after we pass 6, we have something which is in the blue set, but is not anymore in the black set. So it is not in the intersection. So this intersection is again an interval, but starting now at 3 and ending at 6, including 3 and 6. So I think it is really easy if you draw a picture at the number line, then you just see it, what's in one, what's in the other, what's in both, what's just in one of it. Yeah, so that should be really easy. And we have now also in the new version of the lecture notes, which were unfortunately not quite ready for printing, we have nice colored pictures here. So you see here the red or kind of orange, red, brownish set X and the blue set Y. The union is that purple set, and the intersection is also kind of purple here, but on the bottom. So what you do in general, if you see curly brackets, it's a list of elements, and then you just browse through the set element by element, and for the union you take anything what's here, anything what's there, not duplicating. And if you are looking for the intersection, you browse through all elements of A, look if they are also contained in B. If so, then they are elements of the new set called the intersection. It could also be that if no element of A is an element of B, then the intersection is the empty set. No element of A is at the same time in B, or no element of B is at the same time in A, then the intersection is the empty set. So that's pretty much what we needed to know about sets. We will use this notation later, but it should not. It's more or less terminology. It's not much to understand. It is easy, and I think it is useful. Because sets appear everywhere in our world, and it is a bit of abstract thinking. Do you have any questions so far? Yes?
Is there a symbol for the non-inclusive set, so X but not Y?
Yes. I did not introduce that, and we will not use it. You can, if you have a set X and a set Y, and you want to consider a new set of all elements of X which are not contained in Y. The standard notation is actually the backslash. But I don't want to confuse you with that, but if you ask, I tell you. Sometimes in the literature it is also just the minus sign. But more common is the backslash. Also very useful for internet searches, because you may, Google can do that. You can ask for say for U&E, but not Math120. I don't know, don't want to know anything about Math120, U&E, but don't show me the web pages which have Math120 in it. There's also a logic function in Google that allows you to do that. So the next step is functions. Functions is the most central notion of this whole unit. So we will, in one or the other way, everything what we will discuss, maybe except for matrices, but everything will be functions. And functions are mathematical models which do the following thing. You assume you have two measurements. Say one measurement is very simple. You measure time using your clock. So a measurement is, say, maybe it's 9 o'clock, it's 10 o'clock, it's 11 o'clock, it's 12 o'clock, which is already a measurement. And at the same time, you measure something else. For instance, a temperature. So say at 9 o'clock, you have a temperature of 12 degrees. I neglect here the units. Then at 10 it was a bit warmer, and at 11 it was again warmer, and at 12 it cooled down again because there was some cloud or rain or something like this. So you have here the time, one measurement, and the temperature. And you may want to investigate how the temperature depends on time. So this phenomenon in life, science, economics, pharmacy, whatever, when one measurement or one quantity depends on another quantity, can always be modeled in mathematics by a function. And the ingredients of a functions are the following. We have, first of all, our independent variables. Independent, also called input, the input of our function. This is what we stipulate at what times we want to do our measurements. And dependent on when we made our measurement of temperature, we get an output, the dependent variable or the output. So we have a set of inputs which is pretty much in our hands. We have declared what the inputs are, and this depends very much on what you are interested in an experiment. You're doing a scientific experiment or some other observation, and it is more or less your decision when and where do you want to do these measurements. This gives you the inputs. The set of inputs is called the domain of the function. Is the domain of the function. So this is just a word, but whenever you want to model some measurement, something which is going on, first thing you make sure you know when actually and where, for which inputs am I interested what's happening. So this is called the domain. Then for each input of the domain, we have one specific output, one specific measurement, and only one. So if we measure the time at 9, we can only get one result at the same place. Of course, different places is a different matter. But if you measure it at the same place, then we get this particular value. 9 is assigned to 12. We have this assignment. 9 is assigned to 12. 10 is assigned to 14. And so on. A better way to write this would be in a little table, which we have here. So 9 to 12, 10 to 14, 11 to 16, 12 to 14. So this is already, a function. We have inputs. We have a way to assign to each input exactly one output. And we could actually also think of this set of possible outputs, which makes sense if you have a measuring device. The measuring device would have a certain precision and would have a certain scale. So assume you use a thermometer which starts, say, at minus 10 degrees and goes up to 50 degrees in steps of 1. So in this sense, the only possible readings of your thermometer would be minus 10, minus 9, minus 8, and so on until 50. Your thermometer would not allow you to read anything else. So this would be the set of possible outputs, and this set of possible outputs is called the codomain. And while it may be very useful in a particular experiment to think what could be the possible outputs, this would help you to find mistakes. If you end up with some table which has, say, 150 here, you look at it and you say this never could be this must be a mistake. It's probably 10 or someone has done something wrong. So it is useful for very practical purposes, even if you don't use the name codomain, to think what are the possible outputs here. Always think what is reasonable, what is what I expected, and if something unexpected happens, think why this has happened. Either this is a mistake or your expectation was wrong. So the word of codomain does not occur in the textbook. If you read the textbook, it's not there, and you probably won't need it so much for the rest of this unit. But the notion of a domain where a function is defined, where we take our inputs from, is also explained in great detail in the lecture, in the textbook. It's all in the lecture notes, in the printed lecture notes. This is also in the textbook. So a function always starts with a domain and with a kind of a rule which assigns to each input exactly one output. This rule could be a function, a formula, an algebraic formula, and most of the functions we will study in this unit are given by algebraic formulas. So, for instance, for an algebraic formula, if my inputs are, say again, no, don't want big inputs, 1, 2, 3, and 4, then I can produce outputs by applying a formula. Say, call my inputs x. This is very often the case that we call the inputs all by the letter x. So x is browsing through these all possible inputs here, and say the output, which I call y, which is often done. Say it is 2x minus 1, an algebraic formula. If I plug in any of my input values, any element of the domain, into this formula, I can compute the output. So 2 times 1 minus 1 is 1, 2 times 2 minus 1 is 3, 2 times 3 minus 1 is 5. You can already see here a pattern that goes up by 2 because of this 2. We will study this kind of functions next thing, so here just as a very simple example for a formula, we can use a formula to produce the output from the input. Here we used an experiment, a measurement, to produce the output from an input. Of course it would be very nice if we could produce this table of measurements doing something simple like plugging the time into formula. So that would be mathematical modeling. If we find a formula which produces the same table, then we have a mathematical model. And usually dealing with mathematical models is much easier than dealing with reality. So if you want to do an experiment about nuclear explosions, it's much better you have a mathematical model, you do it just on the computer, than doing the actual experiment. Experiments are much more expensive, often dangerous. So if we have a mathematical model, we just plug in a number and a formula, or a computer can do it for you. It's much easier. And also it is much easier to handle just a single algebraic formula than a huge table of measurements. So this was just a very simple table. But you can imagine in reality, if you make a huge experiment, you end up with thousands or millions of such numbers, and you can't even write it down, or if a computer writes it down for you, you get a pile of paper which you can't even look at it. So having a mathematical formula as simple as this, and here now x can be anything. It can be not only the 4 numbers which I wrote down here, but any real number gives me an output. So we can use formulas as opposed to tables to even consider functions which have an infinite set of inputs, an infinite domain. A very important and useful way to look at a function is by its graph. As I said, a function has always pairs of input and output, input and output, input and output. Each such pair we can depict in a coordinate system. A coordinate system is 2 number lines perpendicular to each other. So I have the number line of each input of x and the number line of the outputs y. Now for each pair I can find exactly one point which has the coordinates x and y. I assume that you have seen coordinate system and coordinates before. That should not be a problem. So writing this as a pair, and unfortunately here also the common notation is round parentheses. When I write this, I have in mind the pair of coordinates x and y, not the interval excluding the ends. So the pair of x equals 1, y equals 1, I look for x equals 1 on the x-axis, and for y equals 1 on the y-axis, and I go in a perpendicular way up and vertically and horizontally, and I get a single point. So I can depict this pair of input and output by a single point here. Then I have another pair of input and output, 2, 3. So 2 on the x-axis, 3 on the y-axis, a point like this. And same with 3, 3 and 5, and 4 and 7. So a way to depict this function from the table is to draw just these 4 points, each point for one of the pairs of input and output. And we see already just from looking at the graph, this is called the graph of the function. We see from the graph, first of all, every output is positive, which may be already an interesting information. Sometimes we want to see, is the measurement in a certain range which I expected. Often only positive measurement makes sense, not for temperature, but for say, for weight or for something. And you see immediately, without looking at this table may be, especially big table, may be hard to get an idea what's going on. But if you have it in a graph, you see all these points have positive y values. Nothing is happening in the upper half of the picture. Everything is going on in the higher half. So this function has only positive values, which may be already an important observation. We also see here, as I increase, I go from the left to the right, I increase the inputs, also the outputs go up. So this is called an increasing function. As I said before, we can consider this function not only for our initial domain of 4 inputs, but also for any real x. Any real x. So this is when we write x as an element of R. And it turns out that the result is a straight line. We will discuss this in more detail later, so-called linear functions. If you have some set of data in your experiments and you see that these data line up in a straight line, you're quite happy, because then you say, probably this can be modeled by a linear function, and linear models are the most simple models. So it's always good to have data in a picture which line up into a straight line. So here in this case, we can also say from the picture the points lie on a straight line. Okay. Now we were talking about the set of all possible outputs, but in our table I erased it now, so I think it was 9, 10, 11, 12, and I don't remember, 12, 14. Well, what was it, 15?
No, 16, 14.
It doesn't really matter.
12, 14,
16 and 14 again, yeah. Doesn't matter. So we were discussing that any number between -10 and 50 could occur here, but it didn't. Only 12, 14, 16 and 14 again occurred. -10 did not occur, 8 did not occur. So most of the numbers of the codomain did not actually occur. So we can consider another set, which is called the range of the function, and you will find the word range in the textbook if you read the first chapter of the textbook. Range is the outputs which actually occur, which are actually attained, which are assigned to some input. So the actually attained output. So why is this range important? Say x and y. Why is the range important? If you have such a nice table which assigns to temperature, to time a temperature, you could ask a question, what if I knew the temperature, can I conclude at what time this happened? I have the table, I have the temperatures, can I conclude if I know the time when it was? For an example maybe from forensic science, have we any forensic science students here? No, we had in the past. You could have, say, the temperature of a dead body, and you have a table nice like this, what happens after dead body in a certain outside temperature, and you want to find out when did the murder occur. Then it would be exactly something like going not the right way but the wrong way in this table. We would like to go the wrong way. And now we can ask the question, when is it possible? Suppose we have this nice table. Is it possible to go the wrong way, the opposite way? And you will all understand that there are two simple reasons why this is impossible. When it is impossible. So for instance, if we measure a temperature of 10, we don't find 10 in our downside row, so we can't find any time which would correspond to 10 just because it does not occur. This means that though 10 is in the codomain, is an element of the codomain, but 10 is not an element of the range. So if the codomain is bigger than the range, if we have elements which are not in the range, we cannot invert this procedure, we cannot go backwards for numbers which are not in the range. No matter whether they are in the codomain or not, if they are not in the range, we cannot do it. So, first thing, we cannot invert the function for numbers which are not in the range. And in this sense, it is often very natural to restrict the function just to the range, only consider those outputs which are actually in the range. So sometimes, without saying that, we will have the codomain either being just any real number and not caring much more about it, or we may, for certain purposes, when we want to invert a function, when we want to go the other way, then we may just assume that the codomain is the range. We can only define a function which goes the other way. This is called the inverse function, if it exists. We can only do that if for numbers which occur in this table downstairs. The other problem is, as you can also see in this table, we have 14 twice. If we look up here the number of 14, we do not know, did this occur at 10 or did it occur at 12? So if a number occurs multiple times in the second row, we cannot go backwards because a function always has only one output. So the other obstruction is we cannot invert if two different inputs correspond with the same output. Which is the case here. If neither of these obstruction occurs, we can invert the function just going backwards. Which is what we can do in this example. If, say, our codomain is the set of 1, 3, 5, 7, the range, then we can define an inverse function just by swapping these two lines. So what has happened? We have 1, 3, 5, and 7 now as inputs. The outputs became the new inputs, and the inputs became the new outputs. 1, 2, 3, 4. So here, if we want to define the inverse function on the range, then we just read the table in the opposite way. And here it works because different inputs have different outputs. No output is repeated here. So in this case, we again denote the input by x and the output by y. All what we have to do to invert the function, we read the table in the opposite way. What does it mean in the picture? Maybe it shouldn't have removed it. So we have this picture here. Maybe more precise. So it was 2x minus 1. So as I said, inverting a function basically means to swap the roles of input and output, to swap the roles of x and y. So we have here the x-axis, we have here the y-axis. Of course, we can just change notation. We can write the y here and the x here, and reading the graph from the other side. So looking at the graph from here. This would not be very convenient. And also, can you imagine looking at this picture from this side, then the new x-axis, the old y-axis, the new x-axis goes the wrong way. If I look from here, it should go downwards, but it is upwards. If I say, well, imagine you look from this side, what you see is the following. You see why it is important sometimes to indicate the orientation. The orientation here is wrong. So if I look from this side, what I see is something like this. And it is still wrong, so I have to flip it around this y-axis to get a better picture. So to make it the right way, I need to swap it, and I get something like this. So this would be the graph of the inverse function. And it looks actually also like a straight line, and it looks like a completely valid function. We will investigate this later when we discuss more detailed linear functions. But instead of looking at this in a strange way and then flipping this around, there is a way which is easier in one step. I just say it takes 1 minute. This line is called the bisector. It is here at 45 degrees, so it is just halving this quadrant in halves. And if you flip the whole picture around this red dotted line, then, as you see, the y-axis becomes the x-axis with the right orientation. The x-axis becomes the y-axis, also with the right orientation. And this line flips into that line, which is pretty much, if I have probably I did something wrong here, but this is the right picture. I will come back to this tomorrow.